Thank you, Peggy. Welcome
The
everyone.
conference has been muted.
Using the help of...
Sorry,
IMS.
Anisha, can you restart that because I
Oh, sure.
took a second to mute and unmute the lines.
Okay, sure. So the focus of today's session number 3, is how to support voice using an IMS network. So there are several ways of supporting voice. We can use an IP-based system such as IMS. We can use a legacy circuit switch technology such as the UMTS 1X GSM. But today we will be discussing how IP can be used along with the IMS network to support voice. Briefly, my background, I have graduated from Virginia Tech, and as part of my PhD dissertation, I designed handoff algorithms using neural networks and fuzzy logic. I have worked for Nortel and Huawei in the past, and I have designed various radio resource management algorithms for S95 1X and 1X video products. For almost 7 years, I have been teaching various technologies, LTE, WAMX, UMTS, HSPA, HSPA+, 1X video. Okay, so that's my background in brief. Before we get started, if you could please participate in this quick poll, about 30 seconds, a minute or 30 seconds for this one. The type of work that you are doing. And please participate in all the polls. We appreciate your feedback. Okay, so almost 30% system test integration, 30% customer support. Okay, 20% systems engineering, very good. Okay, in terms of what kind of details you are looking for today? 30 seconds for this question. We will also give you some opportunities to ask questions using the audio bridge, but feel free to maximize the use of question and answers box that we have in live meeting. So I will send you a quick acknowledgement. I will type K for OK, and then at appropriate time I would respond. And we appreciate your questions. Okay. So this is what we have, about 65% medium degree of details and 35 lots of details. Okay. If you want something more than what we present, please ask questions. Okay, so this is what we have planned for today's session. We will explain what voice over LTE is. Voice over LTE would be using the help of an additional network, so-called IMS, IP multimedia subsystem, that connects to the evolved packet system of LTE. So we will introduce various nodes of IMS, the functions that they perform. The protocols that play an important role in supporting voice over IP: session initiation protocol, session description protocol, real-time transport protocol, real-time transport control protocol. So those are the examples of the protocols we would briefly summarize. How do we address the destination for a voice or IP call? What are the main steps in setting up a voice or IP call? And we will see that SIP is the protocol that we use to create signaling messages for call setup. That is the one we have chosen for an IMS-based service solution. Examples of supplementary services that we can support. And toward the end of the session, I will briefly summarize how SMS can be supported in IMS. So those are the main topics that we would cover today. Okay, voice over LTE. Now, what is this voice over LTE? So basically, it is an IMS-based voice over IP solution for LTE. So if you recall, there is no circuit switched core network in LTE. Within the EPC, Evolved Packet Core, the only thing we have is an IP-based packet switch core network. We have nodes such as MME, SGW, PGW, HSS. There is no MSC to be found, no switch. That $1 million piece of equipment is disappearing. So if you make a call, voice call using LTE, we need something that interfaces with PSTN. So in LTE, the standardized solution is to use IMS. So our voice call is no longer a circuit switch voice call. It is a voice or IP call. So our speech is placed inside IP packets, voice or IP packets. And those voice or IP packets are traveling through the radio network, through the core network, and using the help of IMS network, we will be able to have communication between the LTE UE and the outside world. Outside world, maybe someone is using an IP phone or someone is using a landline phone. Either is okay. So using IMS for a voice or IP approach, that is voice or LTE. Now, several companies came together and created a technical profile, so-called One Voice Profile. So this One Voice Profile basically defines the required features that the UE needs to implement, the network needs to implement. Because the IMS itself is extremely flexible. So it is possible that the UE implements one set of features, the network implements another set of features, and still they cannot talk to each other because they implemented different functions, different features. So that's where One Voice Profile comes into the picture. One Voice Profile says, okay, here are the basic items, minimum requirements that everyone should implement. And then we have interoperability between the UE and the network. So that's One Voice Profile. Okay. So here are some examples. For example, we have chosen SIP as the session initiation protocol, which is the protocol we will use to exchange call setup signaling. We will be using UDP, for example, below the RTP, so that we can carry the user traffic, which is voice or IP speech. And then we will use, for example, robust header compression to compress IP headers so that we make our use of air interface very efficient. If you do not do header compression, then your voice or IP payload and the IP header they may be of almost the same size, so it's like 50% overhead. Right? We do not want to do that. LTE is all about efficiency, so we do not want to have 50% overhead. So in that case, we should do the header compression, and we have chosen to use robust header compression. And LTE with voice or IP optimization, for example, the air interface, we will do certain things related to RLC, radio link control, certain things related to MAC hybrid air Curie transmission, things like that we can do to make air interface efficient for voice or IP. So we specify basically what mobile device needs to do, what the radio and the core networks need to do. In terms of the IMS network, again, the UE will be talking to the IMS network, will be supporting certain codecs and certain protocols. So one voice profile says, okay, for all those various layers and various protocols, what should we do? Examples of what we need to do in terms of the medium itself. We have chosen to use adaptive multi-rate speech codec. So if you recall, this is what we have been using in GSM and UMTS networks in current commercial deployments, and we will continue using that for LTE as well. So, for example, even though Verizon and Sprint, they are using 1X network for voice today, and they are using EVRC codec, right? But they will also be moving toward AMR speech codec, adaptive multi-rate, because that's the one we have chosen for voice or IP traffic. So a future handset that supports voice or LTE, that will be having a codec called AMR, adaptive multi-rate speech codec. There are 8 modes, basically different data rates. The one that we expect to be quite popular is the full rate speech codec. Excellent voice quality, 12.2 kilobits per second is the full rate. So we expect that to be quite common. As I said, to reduce the overhead and improve the efficiency, we will use robust header compression. So we have chosen that as the technique to compress IP headers. Now just refreshing your memory, in an LTE system, just use this journal, and I will send you soft copy of these journal notes. So basically, if this is our E node B would be getting a pure IP packet, let's say voice or IP packet. So we would have some IP header, and then the payload that would be coming, let's say, from serving gateway. So voice or IP packet arrived from the outside world to the PGW serving gateway, and now at the E node B. Now, E node B gets this pure, full-fledged IP packet. In 3G technologies, base station never sees an IP packet because we have RNC, that radio network controller is chopping down that IP packet into pieces, RLC, RLP segments. But now, E node B gets this pure IP packet, so it has the visibility of this IP packet, and that is the reason that we need to do header compression at the E node B. In today's networks, if you want to do that, it is done not at the base station, but for example, we can do at the RNC in UMTS and PDSN in 1X eVideo or 1X technology. So robust header compression would now be the responsibility of the E node B, and more specifically the protocol layer, TCP will do that, packet data convergence protocol. That will be doing the header compression. So that's what we will do for reducing the overhead and supporting more users on our existing resources, maybe 10 megahertz bandwidth, maybe 5 megahertz bandwidth. Okay, then in terms of how we will use the medium audio video profile, what kind of audio video profile we should use? We should use a RTP profile, and within an RTP packet, a real-time transport protocol, within one RTP packet, in general we could have placed more than one speech frames, but voice or LTE medium in terms of one voice profile. See, all the requirements that you see here, they are dictated by one voice profile. And we have decided that, okay, in one IP packet, one speech frame would be placed. So if you have an RTP packet, inside that we will place only one speech frame. And remember, the vocoder is generating speech frames every 20 milliseconds, right? So that's the one we will use. Every 20 milliseconds, the AMR speech codec will be generating a speech frame. And then a little bit later, I will mention how we can negotiate quality of service. And if you recall, then within a SIP message, let's say I have some SIP message, so-called invite message. Inside that speech invite message, there would be information about the medium, session description protocol. That will tell us something about QoS. What kind of speech codec we will use, what kind of data rate we will use. So, how to negotiate QoS? So, we will use a specific type of mechanism to negotiate quality of service. We are not using so-called STB capability negotiation framework, but that will become clear a little later. Okay? When we talk about call setup, I will talk more about this. For sending our speech frame or receiving speech frame, we will use the same port number. No need to use different port numbers for sending our speech and receiving our speech. As far as the payload itself is concerned, we can have so-called bandwidth efficient mode or octet aligned mode. Here basically we are reducing the amount of zero padding. In octet aligned, we add enough number of zeros, so we have the number of bits in terms of factor of 8, 16, 32, that kind of number of bits. Now, normally, we will not use RTCP, okay, real-time transport control protocol, except during the media hold, okay. So when we are just talking, right, regular voice call, so we are talking to someone, the other person is listening, sometimes we listen, the other person talks. So for such normal communication, RTCP will not be used, okay. In one voice profile, we have specified that we will use RTCP only when we put the media on hold. So let's say another call comes in and we put the existing call on hold. So only during that time we will start using RTCP. The idea is that we want to minimize the impact on voice quality. Right? So if you're already talking, we are generating speech frames, sometimes we are doing retransmission, and the radio resources are precious. So the available radio resources are used to carry the real speech traffic. Okay. RTCP, we will see later, is just to provide some kind of feedback on the quality of service. So if you are already talking, then we do not want to get some additional feedback like that, because we have a lot of optimizations on the air interface that will make sure that the quality is being met. Okay, so for example, we can guarantee 1% packet error rate. We will guarantee 100 millisecond of delay. So if you recall, then we will have QCI number 1 for our voice or IP traffic. And we will guarantee data rates by reserving certain resource blocks on the air interface. So we have a lot of things we can already use to guarantee QoS. So that's why RTCP is not critical when the call is going on. If you put the media on hold, there is no traffic ongoing, so then you want to get periodic feedback, okay, just to make sure that the connection is alive. So to mimic it alive type mechanism, we will use RTCP to get some kind of feedback, okay, just to keep the link alive, because the media is on hold with a specific user, specific column. So that's why we say that we will not use RTCP except when we put media on hold. So there was a question on that, so hopefully now that is now clear. Okay, then as far as quality of service is concerned, see, first let's step back a little. Now, we do not want to reinvent the wheel. Okay? So whatever work has been done by IETF, Internet Engineering Task Force, we want to reuse that. We do not want to start defining new protocols and things like that in LTE. So what we will do, we will use the work done by IETF, and IETF is not only for us wireless, right? It is for wireline folks, it is for wireless, everyone can use IETF recommendations. They have RFCs, request for comments, and they are basically the specifications. So now we have these quite comprehensive, flexible, generic set of specifications. And now we will modify those. We will simplify those for our LTE application. So that's why you will see that here in voice over LTE, we said, okay, we will use the so-called STP offer answer model. So one end of the conversation, they will, let's say UE1, so they will offer some kind of QoS, let's say QoS 1 and 2. So we are making some kind of offer. The other party may be UE, maybe some landline phone, maybe an IP phone. So that says, okay, here is my answer. I support this kind of QoS. So now we have basically found a common ground between the endpoints of the communications. So we will use that kind of model for voice. Preconditions. Preconditions, I said here, STP capability negotiation framework nodules. So what are we really using then? We are using this kind of approach, that in the set signaling messages, we would use the header called supported. We will not use the header required. Okay? This is just to simplify our implementation. Remember, you want to minimize variations. Otherwise, interoperability would be a nightmare. So we said, okay, use the supported header. And when we are doing the call startup signaling, while originating a call, we will include so-called precondition tag. Why? Because in a wireless system such as LTE, we may not have resources. So if we run out of radio resources, then we do not want to go through the hassle of exchanging lots and lots of signaling messages. Okay, so if you count the number of messages that are flowing through the network from one end to the other end, it is close to 70, lots and lots of signaling messages. So you are not going through all those signaling messages to find out at the end that, oh, we do not have radio resources. Okay? So it's a lot of waste of our processing power, things like that. So what will happen is, as part of the call setup, in the early stage itself, we will make sure that we have resources available. So before we continue spending our efforts in setting up a call, in the early stage of the call, we will make sure that we have adequate amount of radio resources available to support the call. And that's where this precondition text comes into the picture. So until quality of service is satisfied, until we have reserved radio resources to support that kind of call, we will not move forward. So that will make sure that we spend the processing time, processing power wisely. Even though we say that preconditions may or may not be used for all practical purposes, you can assume that the operators such as Verizon, AT&T, they would indeed use the preconditions in the network, so that we make sure that resources are reserved. But this is just to give the operators flexibility, but assume that we would indeed have negotiation of the QoS, we will reserve resources, and then we will continue with the call setup. We will discuss the steps of call setup a little later. Okay. Now, we will discuss various building blocks of supporting voice over LTE. One main building block is IMS network. Voice over LTE uses an IMS-based solution. An operator, in general, does not need IMS to support voice over IP. And we can have our own proprietary solution. We can use even Skype, Yahoo to make a voice over IP call. So, if you just think of voice over IP, yes, we do not need IMS. However, if you use IMS, it becomes a standardized solution. So the operators can be rest assured that the UE and the network would be able to work with each other because they would be following one voice profile. And IMS is used not only for voice over IP, but for many, many other IP-based applications. So using IMS essentially becomes mandatory, okay, because that's what gives the operator a cost-effective and fast way of supporting voice over IP and many, many more IP-based services that are under the control of the operator. So IMS is for operator-controlled IP services such as voice over IP. So that's the trend. Industry is moving toward IMS. So let's see what that IMS network is all about. Okay, so we have this IMS network that is connecting to our LTE core network. This is EPC, AU Trust. So do you remember what happens when you combine EU-TRAN with EPC? What do we call that? The combination of the radio network and the core network. It's a three-letter word. Radio plus core together. EU-TRAN plus EPC. What do we call that? You can answer through Q&A. I see something already. Okay, very good. EPS, correct. So LTE has a radio network plus core network combined, which will be called formally EPS, Evolved Package System. Thank you for your answer. So in the LTE EPS, Evolved Package System, we have radio and the core both. Now, IMS, where does it connect to? It connects to the EPC. So let's take a simple example. We have, let's say, call setup. So as part of the call setup, the UE is generating SIP signaling messages. that will find its way to the E node B to the serving gateway to the PGW. So this is our SIP message. Okay. Such as invite, because we are trying to call someone. We are inviting this, maybe this landline phone. So now our PGW has received this SIP message. The destination of that is proxy call session control function. And in the next few slides, we will talk more about the roles of various IMS entities. So here I am just giving you a high-level view. So the destination of that IP packet is proxy call session control function. So it will be sent to the proxy. Again, this is an IP network of the operator. So AT&T has its own private IP network, Verizon its own IP network, like that. And this is operator's IMS. And the PGW has forwarded that message, SIP message, through the IP network to the proxy call session control function. The proxy forwards that message to the serving call session control function. Serving. So for a given user, there is one call session control function that is in charge of that session. It controls the session. Okay? And how do we know that this is the serving CSCF? In the past, when the UE did IMS registration, as part of that process, we know who the serving CSCF is as part of that process. So now that's the reason proxy is able to forward the IP packet containing a SIP message such as invite to the serving CSCF. Then the serving CSCF looks at the destination party. Whom are we trying to reach? Let's say some landline phone, this number. So it means we have to go outside the IP domain. We have to enter another domain, circuit switch domain, PSTN. So we have to break outside the domain. So it will forward the message to so-called breakout gateway control function, because we are breaking out of the IP domain into some other domain such as PSTN. Now the BGCF, breakout gateway control function, says, okay, I need to go to PSTN, and looks like this phone number, let's say, belongs to this specific area. I will just take an example. Let's say the UE is in Dallas. This is, let's say, Chicago. Is our destination. So the breakout gateway function will pick a media gateway control function that is close to Chicago. Media gateway control function close to Chicago. So think of media gateway control function as MSC server. Okay, it will help us with the call setup signaling. Now this invite message is a SIP message. But our PSTN does not understand SIP signaling. It understands SS7 type signaling. So we need to convert that message into some ISUP message, which will be initial address message. So SS7 ISUP signaling. So the name of the message would be initial address message. So our media gateway control function has now converted a SIP invite message into initial address message. That's for PSTN. It's all IP, still IP. So initial address message still is over IP. Then that initial address message over IP goes to signaling gateway. And remember, this is different from serving gateway. The serving gateway is here. This is serving gateway, which is inside the EPC, LTE EPC. We are not talking about serving gateway. This is signaling gateway, specifically that will convert the IP into lower layers of SS7 protocol stack, message transfer part. So now this is the one PSTN can understand. So finally the message has gone into the PSTN network, landline phone, and then we set up the call. So that is how the SIP signaling message is traveling through the network. Once the call is set up, the other party has answered our our call, then what will happen? Then the media will be traveling. How will the media travel? Okay. The medium is voice over IP. It will go from, let me use a journal so that it is clear. This is already crowded. So the UE to the E node B to the serving gateway to the PGW. So this is all IP. From there, the packet will be going to the media gateway. So let's say the UE is in Dallas. Media gateway control function close to Chicago will choose media gateway that is close to Chicago, because that's where our destination is. So media gateway control function has selected this media gateway close to Chicago, and that will convert our voice or IP into something that PSTN can understand. 64 kilobits per second pulse coded modulation signal. So from Dallas all the way to Chicago, we are consuming tiny bandwidth, maybe 12.2 kilobits per second. AMR is the format, adaptive multi-rate speech format. Only when the voice or IP packet reaches the destination area, here in this example Chicago, then the media gateway will start using the PSTN. So every call made in the voice or IP approach, voice or LTE approach, is a local call, because we enter PSTN only when we are near the destination. So here Dallas to Chicago call, a long distance call, has become a local call. So we can even go across the continent. We can call from US to Australia, and we will start using Australia PSTN when we enter Australia. So from US all the way to Australia, we can use the internet. The IP packets are traveling from US to Australia, and then a media gateway in Australia would convert that IP packet into 64 kbps signal. So that is the beauty of voice over IP, that we are able to cost effectively support voice calls. We have got one question. Who requests the signaling gateway to convert IP to SS7? That will be done by the media gateway control function. So signaling gateway is the box, and that knows that, oh, whenever I receive this SS7 message over IP, I should convert that into the PSTN friendly format, meaning MTP. So lower layers of protocol stack are converted from IP to SS7 and by signaling gateway based on the instructions from the media gateway control function, MGCF, media gateway control function. Okay, so those are basically the signaling paths and the traffic paths for our voice call. So we got some idea about the roles played by all these various IMS entities. As we go through the next few slides, we will be learning a little more about the roles played by various entities. Now it looks like we have a couple of questions in line. The vocoder could be different than the AMR. Okay, now in general, as far as IMS is concerned or voice over IP is concerned, we can use any speech codec. Okay? So UV may be supporting 5 different speech codecs. Another destination may be supporting 3 different codec formats, and we can negotiate which one to use as part of the call setup. However, remember what we said, we want to use voice over LTE, one voice profile. So one voice profile says that right now, what we should use is AMR, speech codec. In future, we may add more speech codec support, but right now, AMR is the one that we have settled on. AMR is the chosen one. Okay, so right now, for all practical purposes, AMR is the one we will use. Okay, who handles echo? Does AMR handle the echo? Normally, we have some separate boxes, entities, right, that will send the ringback tones and echo cancellation. So normally we have some entities, some auxiliary boxes that will help us. So AMR on its own, it just is a speech codec. Okay, so it will convert your regular speech signal, analog speech signal. So let's say I'm talking now, it's an analog signal. So the AMR will convert my analog signal into bits that we send over the air. So speech codec on its own does not do anything with echoes. So we have some separate boxes normally that we use in cellular systems to do the echo cancellation. So AMR itself doesn't do that. So some separate boxes are used to do that. SGW is for call setup signaling. Yeah, it is only for call setup signaling, correct. To extend signaling with PSTN, that is correct. And media gateway is only for traffic or medium. That is absolutely correct. Absolutely correct. So signaling path. Okay. So yeah, maybe this picture a little misleading, but let me show you from the journal. Okay. So here, if you see the voice or IP traffic itself, that it does not pass through MDCF. See, the voice or IP traffic itself, your real speech, is going between UE, E node B, serving gateway, PGW, this is the IP network, media gateway, right? A media gateway into the PSTN. So that is end-to-end part. So MDCF has no role here in forwarding the voice or IP traffic. Now, call setup signaling. Okay, so call signaling. To set up the call, to modify the call, meaning add another party to the call, conference call, add, let's say, something to the call, some kind of, you could say, announcement, things like that. So that is a modification of the call. Then tear down of the call. So all those things that are related to signaling for the call, so that is going like this. And you can go to full screen mode to view the whole journal screen. Okay, F5, function key F5, PGW, and then PGW to the media gateway. So proxy, serving, so it is like that. Okay. So this is a call setup signal. So that is traveling like that. So call setup signaling, yes, it passes through MGCF, media gateway control function, but media itself, for example, voice or whatever, it does not travel through MGCF. So hopefully that clarifies. A couple of more questions are coming. Is there any QoS control from PGW to the media gateway? Oh, this is just an IP network, right? And when an IP packet is traveling through an IP network, what do we use to provide quality of service in the IP world? Do you remember that? In the IP network, how do we provide quality of service? So in yesterday's session, we mentioned something that starts with D. Okay, looks like there is something coming. Oh, DSCP, excellent, excellent. So we use DSCP, right? Differentiated services is the approach that we have chosen. And we will have different code points that will tell the IP router how to treat an incoming IP packet, whether it should forward the packet immediately or can it place that packet in the buffer for a little longer. So yeah, differentiated services, DSCP is the thing that we use to provide QoS in the IP world. Okay. Thank you for your questions. Okay. So now you should have some basic understanding of how we can use the IMS network. Okay. Now, one thing that we have not yet discussed, but there is something called the application servers. Okay. So if it's a simple call, just to simple call between two endpoints, then application server is just informed that, oh, there is this IP call going on between two endpoints. If you want to do some extra things, such as a three-way call, something beyond a simple call, Then we will use the help of this application server to do additional things, even supplementary services, call forwarding, call waiting, message waiting, things like that. All those extra features beyond a normal call are all available as part of the application server. So we can have some application server supporting many kind of features beyond a normal call. But if it is just a two-way call between the endpoints, then we just inform the application server that, by the way, here is some voice or IP call going on between the endpoints. But features can be supported through application servers. So we can have one application server just for voice or IP, and then another application server for gaming, another application server for some kind of location-based services, things like that. So a lot of possibilities to offer IP-based services. SMS, there may be an application server. Presence, like Yahoo, Skype type messengers. So we may have an application server supporting that kind of service. So lot of possibilities. Imagination is the only limitation. Okay, now let's go into the details of various IMS entities. Now, this call session control function. Call session control function. It is basically the brain of the IMS network. There are three logical types of call session control function: proxy call session control function, interrogating call session control function, and the serving call session control function. So those are three types of call session control function. Now these are logical entities, so it is possible that we may have all the three logical entities in a single physical box, or there may be three separate physical boxes containing three logical entities. Standard is very flexible. IMS is very flexible. Now, my colleague Dr. Best has this very nice analogy to understand and remember what those CSCFs are doing. So for that, we need to take a detour to Hollywood. Okay. So we have Tom Hanks, okay, our actor. It plays different roles. So Forrest Gump, remember the movie Forrest Gump? Tom Hanks, Forrest Gump, is everywhere whenever there is some major event. Okay, he's always there. Okay, so whenever something important happening, Forrest Gump is always there. Proxy is always there. Whether you are in your home network or you are roaming, proxy is always there. Always there. So whenever our UE starts sending out SIP signaling messages, they first arrive at the proxy, because proxy will always be there. Think about the movie Philadelphia. Tom Hanks plays the role of a lawyer, an interrogator. What does a lawyer do? Interrogates, right? So, interrogating CSCF will interrogate. It will ask HSS, Home Subscriber Server, which serving CSCF I should choose for this user. So interrogating CSCF will ask or interrogate HSS that which serving CF to choose for that user. Finally, serving. CSCF. So remember the movie Apollo 13. So Tom Hanks is commander of that spaceship, Apollo 13, in charge of that spaceship. So serving CSCF is in charge of the ship session. Okay. So our ship message will find its way to a specific serving CSCF, and serving CSCF is in charge of that session. For example, it will decide, has the user subscribed to this kind of application? How do I authenticate the user? So it will exchange authentication messages with the endpoint. So it is in charge of that session. It will authenticate the session. So in summary, Tom Hanks in the movie Forrest Gump, that's proxy, always there. First point of contact of UE with the IMS network. Interrogating CSM. Lawyer Tom Hanks in the movie Philadelphia. It means it interrogates the HSS, that which serving CSCF I should pick. And finally, serving CSCF is in charge of the session. It does the authentication. So that's a high-level summary of 3 different types of call session control functions. So let's go into the details now. So proxy, as we mentioned, it is the first point of contact of UE with the IMS network. Okay. And when the UE does the attach operation with LTE, for example, UE sends a message, power-up message, after some time attach a request. That message will find its way to the MME, Mobility Management Entity, and the MME says, oh, okay, attach accept, after we take care of authentication, etc. Inside that, we will tell the UE, okay, here is the IP address of the proxy call session control function. So when the UE performs power up initial LTE attach, as part of that attach operation, UE learns about the IP address of the proxy. So in future, whenever our UE constructs SIP signaling messages, the source would be UE, the destination would be proxy call session control function. So now we are able to communicate with the proxy. The proxy will be forwarding call setup messages to a specific serving CSCF, and that will happen as part of the IMS registration. Then we have emergency services. Okay. So when someone makes a 911 call using IMS using LTE, then the proxy will know that, oh, this is an emergency message. Let me forward that to a suitable network element, some kind of emergency call session control function that will interface with the public safety answering point. Security and quality of service, very, very important. Security. So if we want, we can do encryption. Between the UE and the proxy. So the signaling exchange or whatever we are doing, that is all secure. So if we want, we can do encryption between 2 endpoints, UE and the proxy. So in between, eNodeB, serving gateway, PGW, they are just forwarding encrypted SIP signaling messages. So that is available as an option. Quality of service, again, very, very important. We will see that proxy helps with QoS negotiation. The proxy plays an important role in the negotiation of QoS between 2 endpoints. and we will talk more about that just a little later. Another important function that proxy can do is compression. This will reduce the size of messages. See, our SIP signaling messages, they are text messages, right? We have ASCII characters. So our messages can be thousands and thousands of bits long, if not thousands, hundreds and hundreds of bits. So if you want to make efficient use of air interface, then you can compress those SIP signaling messages. So between the UE and the proxy, we can do SIP compression. So over the air, we are using few bits rather than hundreds and thousands of bits. We have now reduced the size of SIP signaling messages. So SIP compression is also possible, and the proxy will do that. That is just making the air interface use more efficient. So those are the examples of functions performed by proxy. Remember that is forest term is always there, whether you are roaming or in your home network. The first IMS element the UE talks to is proxy. We had got one question. Does proxy then talk to proxy of home network or interrogating? It will talk to interrogating of the home network. So proxy of a visited network talks to interrogating of home network. Okay. Okay. Let's go to the next. CSC of interrogating. So it interrogates, asks HSS. So here is the proxy. It sends some kind of message, let's say register message. So let's say UE has done LTE attach. So after we have done the attach operation, then we can do the IMS registration. Okay, so as part of the IMS registration, the UE sends a message, SIP request called register. This is a SIP message, register. So register message has reached the proxy. So E node B serving gateway, PGW, etc. From PGW to the proxy. Now the proxy will forward that register message to the interrogating CSCF. Now interrogating will interrogate HSS that which serving CSCF should I contact for that UE. So HSS says, okay, the one that has IP address X. So now the interrogating will contact the serving CSCF that has an IP address X. So this is one possible implementation. So what does interrogating do? It can choose the serving CSCF based on the instructions coming from the HSS. Load balancing, there may be multiple serving CFs, and all of them are capable of supporting the UE. So then it can choose a serving CSCF that is lightly loaded, fewer users. So it can do that. Topology hiding. Thing. Topology hiding. So-called thing. So what is that? See, normally if you look at SIP signaling messages, then inside the SIP signaling messages, you will see the entire path traversed by that SIP signaling message. For example, it will say it went from node 1 to node 2 to node 3, node 4, right? You can get the whole end-to-end path by observing SIP signaling messages. So if you do not want others to find out your internal network topology, then you can do that by using the help of interrogating. So the path for the overall SIP signaling message is now encrypted. So you cannot go inside the SIP signaling message and figure out what internal architecture of some service operator is. So that is called topology hiding. Okay, not revealing the internal architecture of the network, because there may be several nodes, let's say some routers here, here. Okay, so if you do not want others to figure out the internal architecture of the network, then you can do topology hiding. So then interrogating can activate that and encrypt the headers so that the topology is not disclosed to others. So those are examples of the functions that interrogating carries out. So interrogating is always in the home network, okay? And the proxy could be visited or home. Okay. So interrogating is always inside the home network. So serving different serving CSCFs may have different capabilities. So in this example, we have capabilities A, B, C, another serving CSCF, A, B, another serving CF. Those are the capabilities. So if we are looking for capability A, let's say regular session control, then we can choose any of those three. So then we can do load balancing across the serving CSCF. Also, the serving CSCF acts as a registrar, meaning it will do the authentication. This is IMS authentication. So MME does its own authentication, and serving CSCF will do its own authentication. Okay, it's for IMS purpose, IMS registration. Now we got one question: how does the MME know what proxy CSF address to put in the accept message? Very good, very good. So this MME belongs to the visited network, right? So MME, let's say, belongs to operator X. Okay. So this operator X has the proxy IP address, let's say Y. So MME knows that, okay, in my network, here is the IP address of the proxy, because it belongs to this operator X. Operator X owns both MME and the proxy. So one simple way is we can put that kind of information in the database, in the MME. Okay, that the IP address of the proxy is this Y. Okay. So there is one way we can configure the MME database with that kind of information, or so that's one way, directly provisioning the database based on our operator configuration, or we can use the help of DNS, domain name system server. So MME can ask DNS that I'm trying to reach proxy, right? And then DNS will come back with the IP address of the proxy. So let's say the user says I want to okay, UE belongs to, let's say, xyz.com. So the MME can ask the DNS server that I want a proxy for xyz.com, and then the DNS can come back with the IP address of the proxy, call session control. Those are two examples through which we can figure out the IP address of the proxy, and that IP address of the proxy is indicated to the UE as part of the attach accept message. Thanks for your question. Good question. Okay. Okay, so we looked at the call session control function proxy, interrogating and serving. Let's take a short break, and once we come back from the break, we will continue with our discussion of IMS elements. So we will start a 10-minute break now. What I have got. So one question is why MME has knowledge about proxy? Okay, so as far as communication is concerned, okay, if you look at the signaling here, call setup signaling, okay, SIPs-based signaling, that is going from PGW to the proxy, etc. So MME does not come into the picture here, okay, because SIP signaling is treated like user traffic. However, we need some way of informing the UE who the proxy call session control function is. We need to give the UE IP address of that proxy. That is the reason that as part of the attach operation, we are providing that proxy IP address to the UE, and MME needs to do that because attach accept message is constructed by MME. So somehow MME needs to find out the IP address of the proxy, right? Because only after it knows about the proxy address, it can put that address in the attach accept message. And I mentioned two possible ways. There may be more than two, but at least two ways. One way is just configure the MME database with the IP address of the proxy, so we can put that address into the attach accept message, or MME can just use the help of DNS to find the IP address. MME doesn't need to communicate with the proxy. Okay, there is no need to do that. So call setup signaling, we don't have to worry about MME and proxy interactions. MME just needs to somehow figure out the IP address. That's it. So hopefully that is clear. And then there is a question. MME's DNS capability is a standard requirement or implementation option? Just the option. It is an implementation option. It is up to the operator what method it wants to use to get the IP address of proxy. So again, 100% implementation specific. Then there is a question about the register message. For every new call, do we need to send register? Oh no, registration is not for every new call. Registration is, think of that like attach operation in LTE. So UE does attach when it does power up, right? Power up registration, that is your LTE attach. So just like that, when the UE has a basic connectivity with the LTE EPS, meaning it has taken care of the attach operation. We have default bearer setup, perhaps even some dedicated bearers have been set up. Then it communicates with the IMS network. So the first time it communicates with the IMS network after power up attach operation, then it will do the registration. Once you have done the registration, you are all set. Okay, then you don't have to worry about doing registration for every new call. That will be too much. Okay, that will be too much. Excessive signaling. We want to avoid that. So hopefully that is clear. Okay. Okay. So let's give you a chance to use the audio bridge if you wish. So *7 unmute and *6 to mute. So *7 unmute. So I will wait for 30 seconds. If you have any questions that you would like to ask through the audio bridge. So *7 unmute. Anyone who would like to use the audio bridge? 10 more seconds. Okay. Please continue relying upon the Q&A facility in live meeting to submit your questions. And as always, your questions are most welcome. It will help you, your colleagues, and me. So please maximize the use of Q&A feature from live meeting. Okay, so continuing with our discussion of IMS elements. Now we talked about HSS in session 1. Okay, so as part of the LTE attach operation, MME works with the HSS to do the authentication. Okay, we can also use that to generate some keys for security. For example, we can do encryption, we can do integrity protection. So all the things are related to LTE. Okay. Now, specific to IMS, HSS has additional responsibilities. So, for example, it can provide the subscription information to the serving CSCF. So we can do IMS authentication. We know what IMS capabilities UE can use. Then interrogating, it will ask HSS which serving should it pick for that user. So application server also can talk to the HSS to figure out about UE's capabilities. So those are some extra functions that HSS has to perform by supporting those various interfaces. But again, it's a database containing subscriber information. Okay, media gateway control function. So media gateway control function, on one end, it accepts SIP signaling messages such as invite, and on the other hand, it talks the ISUP language, for example, initial address message. So it converted a SIP message into an ISUP message and vice versa. It also controls the media gateways. So if we are talking to, let's say, San Diego, then media gateway close to San Diego will be chosen. So one function of MGCF is to pick the media gateway closest to the destination. And it will tell the media gateway that, okay, you can expect voice or IP on one side, and then you will have to convert into PSTN type signal on the other end. So those kinds of configuration instructions will be conveyed to the media gateway by the media gateway control function. Now it is possible that those two functions are in the same box. Okay. But media grade control function is just for signaling. Okay? Traffic does not pass through the MGCF. Traffic is only passing through the media gateway. So here is the example that I referred to earlier. On one side of the media gateway, in our voice or LTE case, it would be AMR speech frame, probably 12.2 kbps. That would be the most common deployment configuration. So on one side we have voice or IP in the format of AMR, and the other side would be pulse coded modulation signal, and that's the one PSTN can understand. So on the other side you will see much higher data rate, because that's the one PSTN understands. So that's what it will do, conversion between two formats for the medium. And the media gateway control function will actually configure the media gateway with that kind of conversion. Finally, we have so-called application servers. We have different kinds of application servers. These would be the most common application servers. So it is SIP-based application server. So maybe we have one server for voice or IP. This is directly controlled by operator. So whether you want to do SMS or presence or voice or IP, operator can control those application servers, or third party can manage the application server. So we have some kind of interface that we need between the third party application server and the IMS network, our operator's IMS network. So there's this box. Okay. So we can provide, for example, security, because maybe this is passing through the regular internet, so we can secure that interface. And then if you want to provide intelligent network services, for example 800 dialing, etc., then we can use the service switching function for IP multimedia, service control point, that is to support some legacy service. But for our purpose, this is the one we are interested in. We would have some application server that would be supporting voice or IP and related services. Okay, time for me to ask you a question. So please give me your answer. True or false? Should be easy. At least 50% chance of getting it right. So hopefully you have been paying attention. So you should be able to get this right. Uh, 30 seconds to go. And please participate in all the polls. Okay. Let's share the results. So close to 90% got it right. So it is true. Because see, IMS itself is so flexible, so comprehensive that it is very, very easy to miss some features. So we may have one set of features, network another set of features. There may not be any common ground, and then there is no interoperability, even though both are following the standard. Because a lot of things are optional. Many, many ways of doing the same thing. So we want some minimum requirements. that everyone should follow. Okay, application server. Application server, what do you think it does? I will give you about 1 minute for this one. Okay, about 85% got it right. So, for example, they can support SIP-based applications such as voice over IP, SMS, reasons, converting media from one format to another, that is media gateway, first point of contact in the home network. Okay, first IMS contact, that is the proxy, CSCF, and in the home network it is interrogating CSCF, and who will act as registrar, that would be serving CSCF, because serving CSCF would be authenticating the user for IMS services. Okay. The next few minutes we would spend on various protocols. So when we have a voice over IP call, we need some protocols to support signaling. We need some protocols to help with the medium itself, voice medium. So let's see what those protocols are doing. User plane. So we have basically for voice over IP traffic, we will use RTP, real-time transport protocol. In case we have some media on hold, we will use control protocol. For SIP signaling, for call setup signaling, we are using SIP. Inside SIP, we will have session description protocol. Okay. And the protocol stack, so any physical layer, any link layer is okay. Standard does not say anything. IP is here layer 3. And on the top, the UDP is the main protocol. Sometimes we use HTTP, but UDP is the main one that we will use to reduce delay and for efficiency. We will use UDP. Okay. Now, SIP. How do we use SIP? So we have chosen to use SIP for signaling. So IMS network, which is basically defined by 3GPP, is using SIP. So we said, okay, let's continue using that SIP protocol for call session setup. So here, Alice is trying to reach Bob. So Bob and Alice, they are very famous, okay? They are part of the RFC that describes SIP signaling for call setup. That's why you will see Bob and Alice a lot of times. So Alice is making a call, trying to reach Bob. So the first message that we send for call setup is invite message. Okay. So Alice is inviting Bob for a voice or IP call. In general, it could be any multimedia call, but here we are interested in voice. So it's a voice or IP call. So there is a SIP message, invite message, and Once that message reaches Bob, Bob's UE would send back some kind of response. Here we have simplified. Okay? So it's ringing. Okay, we are ringing the device or displaying the message on the Bob's UE that there is some incoming call. And then once the call is answered, and then the response is okay. So that is the response to the invite message. Okay. And Alice is telling Bob that I received okay message. So this is that acknowledgement. So now at this point, call is set. Then the media can flow between the endpoints. Okay, so it's all IP. So voice or IP packets are traveling between the endpoints. In call messaging, maybe we would like to add a text message, add some kind of video, whatever we want to do, we can do that. Photograph, we can add some image. So whatever we want to do, we can do that. And once the call is over, then bye message is created. So here Alice is ending the communication, so she's sending this bye message, and the response to bye message is this okay message. Now the call is over. So that is basically a high-level view of signaling exchange between two endpoints. So these are all SIP messages. As far as the LTE network is concerned, SIP messages are treated like regular user traffic. So they will be passing through eNode B serving gateway, PGW, and the internet. So SIP. As you can see, how are we using SIP? We are using SIP to set up the call, to modify the call, to end the call. So basically, all related signaling. And for that, we have a variety of SIP messages, requests, and responses as shown here. So this is one protocol, very, very important, SIP. Next protocol is SDP, Session Description Protocol. Actually, it's a supporting protocol. Okay, so we put a SDP inside this SIP message. So there is a SIP message called invite. Inside the invite, we are inserting SDP. So as an example, we say that we will use what kind of medium. So here there are different protocols that we have mentioned for the medium. This is 64 kbps signal. Okay. But what we will use is AMR speech codec. AMR speech codec. So SDP would indicate the type of media. Okay, so if you are following one voice profile, then we know that we will pick the AMR speech codec. Okay. We got one question on the buy is hang up. Yes, yes. So Bob will respond because the SIP signaling. When there is some request, you have to respond. So yeah, Bob has to respond. Yes. Okay, because hang up, so call is over. So you need to know, the other party needs to know the call is really over. Okay. We do not want to hold on to the handset. The call is already gone. Okay, so yes, we do need the response. Yes, request and response, they are always there. If there is a request, there would be response. Okay. You have a Newton's law. Action reaction is just like that. Request and response. It is there. Okay, so that's the medium. What kind of format we will use? What protocols we will use? So we will use RTP to carry our voice over IP traffic. Below RTP we will use UDP. So those are specified. Port numbers. So we will specify what port we will use. So if you recall, then in an earlier session we talked about TFT, traffic flow template. So this basically helps us figure out, for example, which GTP tunnel. So at the PGW, we use traffic flow templates to figure out which GTP tunnel should be used to carry a specific IP packet. So we mentioned at the time port numbers. So as an example, port number 2000, maybe that corresponds to voice or IP packet. Now that is specified by SDP. So as part of the call setup, the proxy call session control function, which acts as application function, it will extract STP and then it will work with the PCRF to provide quality of service. Right? So when we extract STP, we learn about the type of medium. If actually this is requested quality of service, we learn about what application this is. So voice or IP, this medium is associated with specific port number. So then now we have relationship and association between the port number and the specific application. What kind of medium? Audio, video, text, etc. So for voice or IP, regular call, the type of medium would be audio. What IP address we will use for communications, that is also specified. We can use IPv4, IPv6, both are supported. So in summary, inside a SIP message, we find session description protocol that describes the medium. Okay. So for one voice profile, it would be 12.2 kbps AMR speech codec. Specific port numbers would also be present. Okay. Another protocol, RTP. Real-time transport protocol, RTP. Okay. Now, we are no longer using a circuit switch voice call. It is a voice or IP call. So it means that we need to somehow put our AMR speech into an IP package. So, basically, we have 12.2 kilobits per second. That is the full rate. In 20 milliseconds, that turns out to be 244 bits basically. Right? So that is our payload, right? Voice or IP payload. That's the number of bits we need to send. Now, those bits are now placed inside an RTP packet. So we add this header. And then RTP will be going into the lower layer. So UDP is adding its own header, and then the IP. IP will add its own header. Okay. So RTP is helping us place the speech bits inside an IP packet. That is the function of the RTP. Now, how does it help the communication? This is an IP packet, so it is possible that some IP packet comes early, some comes little late. So we can never guarantee a fixed time of arrival. It is not a circuit. In a circuit switch world, we have one speech frame, another speech frame, another speech frame. This is a circuit. So it is always that. However, the IP world is different, right? So packets can come out of order, some packets may never come, things like that. So we need the help of some protocol to put together the packets in order, in sequence. We need to know when to play back that speech. Once the receiver gets the voice or IP packet, it will put that in the buffer, and then it will play the voice or IP packet with a certain sequence, with certain periodicity. Okay, because if you think about it, as far as LTE is concerned, over the air interface, we will get the packet in 1 millisecond subframe. Okay, so our 20 milliseconds worth of speech is already received inside 1 millisecond subframe. So now, after some time we'll get another packet, after some time another packet. So we need to now play back all those voice or IP packets. And to help us do that, we have several things. We have timestamps. Okay. So now we make sure that we use that to play back voice periodically and sequence numbers, so we can put them back in the order. So in future, we can have multiple types of stream, and we can put all those together. We can add different kinds of medium. Instead of just AMR speech, maybe we can add something else, add music or whatever. So we can do a lot of different things with RTP. And RTP is running over UDP because you do not want to do retransmission here. It's too much. If you use a TCP will be doing retransmission, and TCP retransmission delay is on the order of seconds. You do not want to play back voice a couple of seconds later. The voice quality would sound terrible. And that's the reason we want to use UDP, no retransmission. Not only that, less overhead compared to TCP. I think 8 bytes instead of 20 bytes, something like that. And of course, do not forget our header compression, right? We will be able to do header compression at the IP layer. The robust header compression will be done by eNode B when this IP packet is fully created. Okay. Now, RTCP, this is just for the sake of completeness. For a normal ongoing call, we do not have to worry about this. So, two parties talking, no need to worry about this because the medium is already flowing, voice or IP packets are flowing. However, if you put a party on hold, then no traffic is coming, right? So, in that case, we want to make sure the link is alive. So, for such keep alive purpose, in voice or LTE, we use RTCP, so that is a control protocol. The control protocol. So what are we doing with the control protocol? So basically there is feedback on the quality of service. So the sender is sending some reports, the receiver is sending some reports, and what do those reports include? Information about the quality of service. For example, the sender would say how many packets it has transmitted. The receiver would say how many packets got lost. What is the difference in arrival of various packets, that is the jitter. So all those things are present in the report, and accordingly maybe in future we can change the parameters. Maybe we can use a lower data rate and do heavy channel coding, or to provide better quality, or let's say CD type quality. Maybe we can increase the data rate if the radio resources are not an issue, things like that. But that's in future. For now, we are just using this for media on hold, but in general, in future, we may choose the different codec and things like that for better quality. So potentially this has other implications, but for one voice profile, the scope is quite narrow, just to make sure the link is alive. Okay, time for a question. I will give you a minute or two on this one. Please participate in the poll. So far I have about 33 responses. We have 60 students. So please participate. Very easy. Just click on a button. So the basic question is, do we use a TCP or UDP, right? For voice, do you want to do retransmission after a couple of seconds or not? That is the question. 30 seconds. So my begging does have some effect. So we have a few more participants for the poll. Very good. Excellent. Let's look at the results. Okay, about 85% correct. So RTP does not use TCP. Okay, so we use UDP. So I mentioned here. Okay. RTP is going over UDP because you want to reduce delay. You do not want to do retransmission. No retransmission. Let me no retransmission. Okay. Because by the time TCP figures out that we are missing a packet, several seconds may have already elapsed, and that's why no TCP to carry real-time voice traffic. Okay, thank you. Now, we go into little more details of how to set up a voice over IP call. I'd give you an extremely high-level view, maybe 64,000 feet view, but now we are getting more specific. Okay, now when we make a call, we have to identify the user, the party, the destination party that we are trying to reach. So how do we do that? So here is just one example. So we are saying here that, okay, SIP, this is the number that we are trying to reach. The context, some LTE operator, and this is phone. Okay, so we are using some phone number to reach the user. And if you look at this structure, like this identity, this is public identity, public. Okay, so public identity of the person we are trying to reach. Now, there are also so-called private identities. So if you recall, every subscriber has a private identity called IMSI. But we do not want to use IMSI as far as possible. Okay? we want to minimize the use of IMSI. We do not want anyone to get our IMSI, because based on IMSI there are a lot of other things, right? So we want to protect IMSI. So that's why we use that only once in a while. For example, registration, we have to use that. But normally we avoid the use of IMSI. So the private identity, which is known to the operator, known to the user, that is a function of IMSI. So something like this is created from IMSI, International Mobile Subscriber Identity. So inside there we have mobile network code, mobile country code, and within that operator's network there will be some number assigned to the subscriber. So we create some private identity like that based on IMSI. But when we send a message to contact the other party, we do not put the private identity for that user. We identify the user by some public identity. So some kind of phone number will be present. Okay. Now, here are the main steps of supporting voice or IP call. So private identity is basically, we got a question. So it is stored on the SIM card, IMSI. So IMSI is on the SIM card. In fact, there is something called ISIM, IMS, Subscriber Identity Module. So it knows about IMS. So IMS specific identities are stored there. So yes, it is on the SIM card, ISIM. Okay. So first, I will give you a high-level view of the call setup, and once that is done, then we will go into the details of various steps. Okay, so we have user 1, IP phone, such as UE. Okay. Now, what are prerequisites? So, in the past, the users 1 and 2 here, they have already done registration. As part of the registration, the serving CSCF has already authenticated the user, and we know who the serving CSCF is. As part of the attach operation, the UE knows about the proxy. Okay. So that's all the prerequisites done. So this serving CSCF is taking care of this user. Similarly, the other UE is controlled by serving CF number 2. So UE1 is known to the serving CSCF1 in the proxy number 1, and UE2 knows about the proxy and the serving CSCF number 2. So that's all done in the past. Now we want to make a call. So let's say user 1 makes a call. So the invite message would now be constructed. So it will go to the proxy. Okay? The destination, the first destination from the IMS perspective is the proxy. The proxy knows that serving CSCF1 is in charge of the user. So now invite message has reached serving CSCF. Here we are not going into another domain. This is IP to IP, UE1 to UE2 phone call. So no need to worry about the media gateway control function or the media gateway. MGCF and MGW, they come into the picture only. We are going outside the IP domain. So from IP domain, let's say LTE, EPS, we go into the PSTN, then we need MGCF and MGW. Here we are staying within IP domain. LTE to LTE, no need to worry about MGCF and MGW. So what should we do next? Invite message has reached serving CF number 1. So now we let's say this is abc.com. And this user, another operator, let's say xyz.com. Now, our serving will have to contact this xyz.com. This is abc.com. Right, so we can ask interrogating guy. Okay, I want to contact xyz.com. Right? So which and I have specific user, right? user2@xyz.com. So who is in charge of that user? So interrogating will say, okay, this is the serving CF number 2 in charge of that user. So now invite message can go to the serving CF number 2. Serving knows who is the proxy, right, in charge of the user. So invite message can now go this way, and then finally the user. So this is basically the main point, main nodes that process the tip signaling messages. So UE to proxy to serving, serving to serving, serving to proxy, proxy to the user. That is sort of the main set of nodes that would be in the signaling path for that call. The other party, user number 2, received this invite message, and now first we negotiate the medium. So let's say speech, we want to use speech, and for the speech we say, okay, what kind of QoS we want to use. Once that is decided, both parties agree on one specific quality of service, then UE1 works with its own LTE network to reserve the resources to support that call, and UE2 works with its own LTE network to reserve the resources. Once the resources are reserved to support that voice or IP call, then the call can move forward. We ring the device. If it's a laptop type stuff, we can display message also. Once the destination party answers the call, then the call setup is over, and then the media can flow between the two endpoints. So those are basically the main steps in case of IP to IP call. We have got one question. In this example, where is the proxy? In this example, what is happening is user 1 is also roaming, user 2 is also roaming. So both users are roaming, basically. So, for example, this could be operator X, this is operator Y, this is operator A, operator B, like that. Okay. So user 1 is actually subscriber of operator Y. And user 2 is this xyz.com, which is operator A. So user 1 has subscribed to operator Y services, and user 2 has subscribed to operator A services. But those users are right now not in their own home networks. They are visiting, they are roaming somewhere. So proxy is now inside the operator X network. Proxy number 2 is inside visited network number 2. Okay. So both are roaming. Okay. Okay, we got one more question. The EPS resources would be reserved by proxy. Absolutely correct. You remembered that correctly. Yes. UE cannot request a dedicated bearer. Yes, yes. So let me just summarize that. That is a very good point. You remember right from yesterday's session. So basically what is happening is the UE is exchanging SIP signaling. It is passing through the proxy, which acts as application function. So once the QoS is known, agreed, you could say negotiated, so once the proxy knows about the negotiated quality of service, then it will work with PCRF. PCRF will ask HSS, do we have enough? Do we have subscription for that service? Assuming that everything is okay, it will ask the enforcement function PGW that I need QCI1, I need guaranteed bitrate, this is a voice or IP call, and then we have other entities. So PGW says, oh, I need a new dedicated EPS bearer because the existing bearers cannot meet this kind of QoS requirements. So the bearer setup request goes this way. MME will work with eNode B, SDW, etc. So that now we have new radio bearer, new S1 user plane bearer, and new S5, S8 bearer. The combination of all those from UE all the way to the PGW, that is nothing but EPS bearer. So as you can see here, PCRF controls the QoS based on the STP information that we extract from SIP signaling. So proxy plays an important role in QoS because it extracts the STP and gives that to the PCRF. So UE cannot make a request for a dedicated bearer, as you correctly remember. Okay. That's the reservation of QoS initiated by proxy, and then PGW sets up basically a new EPS bearer, dedicated EPS bearer. Okay, so those are the steps. Let's go into the details of those various steps. Okay, so the message that user has created is invite, and that invite message indicates what kind of codecs that you even supports. And user 2 responds with the code 183. So this is called request. SIP request. That request is invite. And SIP response. So request and response, those are the formal terms. as far as SIP is concerned. So SIP response is code number 183, and code number 183 means it is a session progress message. So this is the set of codecs user 2 supports. So now we have to find the common ground. AMR, adaptive multirate, this is the one we have chosen for our voice over LTE, one voice profile. ILV say that internet low bitrate codec. It is sort of royalty free. You can use that for free without paying anybody. So that's developed by some global IP solutions, something like that, a company like that. But in one voice profile, we have chosen AMR as the speech codec. Then, if you recall, we have QoS preconditions. Right? So here we say that, oh, we have not yet reserved resources for quality of service. So now, the user one looks at the common codecs. So both are common, so it has to pick one of the two. So it has chosen AMR. In fact, that's the one we will use in voice over LTE. And there's the provisional acknowledgement. Request message again going to the other end. So now this user says, okay, now I need to reserve resources for AMR. In the meantime, UE1 has to work with its own access network, LTE, for example, to get that reservation done. So in LTE, our proxy would learn about the agreed quality of service by observing provisional acknowledgement message. So here we say request resources, but more accurately speaking, proxy has observed these provisional acknowledgement that indicates the agreed negotiated QoS, AMR 12.2 as an example. And based on that, the proxy would work with PCRF, etc., to initiate a new dedicated bearer setup. So the proxy is the one that is extracting QoS. The UE doesn't really formally make a request for resources. It is all implicit. It is all done by the network. Once the provisional acknowledgement is received, response to that is 200 OK. We are still saying that we are working on reservation of resources. We have got a couple of questions and we will answer those soon. So 200 OK, this is the response code that corresponds to OK message. And once the reservation is done, then meaning in LTE, a dedicated bearer setup done. Once the dedicated EPS bearer is set up that can meet QoS for this new voice or IP call, then the UE sends a message, update message, update. Okay, and tells the other party that the quality of service, no problem. We have made the reservation of resources. So we are okay from user one side. Similarly, User 2 says my quality of service is also done. My dedicated bearer is also set up if it's an LTE. So then it will respond with the code number 200. Now both parties know that quality of service has been taken care of. Once that is done, we move forward with remaining signaling exchange. So, for example, we have ringing, the other party would pick up the phone, then there would be an acknowledgement message, etc. So that's basically how we can set up a voice or IP call between two UEs or between two IP phones. At least one is LTE, because LTE would have to have dedicated bearer, etc. Let's answer the questions that we have got recently. Who makes the final decision of AMR? The originating party makes the final decision. In this case, whoever sent the first invite message, that is the party that will be making the final decision on speech codec. So here user 1 has sent the invite message, so user 1 is making the final decision. So that is the key. Okay. There are two HSSs, one in the IMS and one in EPC. Oh, I see. Okay. So this HSS, Home Subscriber Server, it is a logical entity. Now, that HSS has certain responsibilities as far as LTE EPC is concerned. For example, HSS in LTE has to talk to MME so that MME can authenticate the UE. Also, we generate some security related keys, encryption key, integrity protection key. Those kinds of keys are generated using the help of HSS. Now, those functions are LTE HSS functions. So, if we never use IMS, then that is good enough. However, when the operator has deployed an IMS network, which we expect to be the case in the coming years, then HSS has additional responsibilities as far as IMS is concerned. So, for example, it will talk to the interrogating CSCF and tell the interrogating CSCF that choose serving CSCF number 5. It will tell the serving CSCF that, okay, here is a subscriber profile for this user. So HSS has additional responsibilities. It has to support the new interfaces toward interrogating, serving CSCF, etc. So in real world, there will be one physical box, and that one physical box will act as LTE HSS. It will act as IMS HSS. So in practice, a single box will do functions related to LTE EPC and related to the IMS network. So hopefully that is now very clear. Again, as I have said in the past, anytime you want better explanation or you want additional details, please ask follow-up questions. If I do not get any follow-up questions, I will assume that you got your answer, okay? And again, we welcome your questions. We appreciate those questions, so keep sending those questions through a Q&A facility, okay? Okay, let me just make sure we answered everything so far. So far, so good. Okay, let's move forward. Okay, so as far as the LTE is concerned, this is how we take care of dedicated bearer setup for the new voice or IP call. So at this point, what is happening is SIP signaling is in progress, and provisional acknowledgement is the quality of service that is agreed upon by two endpoints, and that is this message here. The provisional acknowledgement. So in fact, we can even do that at this point, okay, session progress, because our proxy is sitting in between. So for LTE, we will have AMR, right? That is the given. So if user 1 says AMR, user 2 says AMR, then proxy can start initiating the dedicated bearer setup by working with other entities. So we can even do that at this point, session progress. But anyway, either session progress or provisional acknowledgement, that is the one here. Provisional acknowledgement or session progress has the same information because the other party has already responded. Okay, so at this point, our proxy, call session control function, which acts as an application function, already knows about the QoS, and it will give that information in the form of STP to the policy and charging rules function. PCRF will tell the enforcement function, which is implemented by the PGW. It will say that, okay, we need certain QCI, we need certain data rate guarantee, guaranteed bit rate, and PGW will work with the serving gateway. Serving gateway will forward the request to the MME. MMA will request the eNode B to create a new dedicated EPS bearer. And inside the new dedicated bearer setup messages, we will include the quality of service that two endpoints have agreed upon. The eNode B now looks at the required quality of service and it checks, do I have enough resource blocks available to support this kind of data rate, to support delay of less than 100 milliseconds end to end. Actually, out of 100 milliseconds, 20 milliseconds is the target for eNode B and the PGW, and the remaining 80 milliseconds is for the radio network. So eNode B just needs to make sure that it can take care of the traffic within 80 milliseconds of delay. So once it has enough resources and it is comfortable that it can meet the delay requirements, it will reconfigure the radio resource control connection, RRC connection, so that we have new data radio bearer. Between the UE and eNode B, a new S1 user plane bearer. Between the eNode B and the serving gateway, and the new S5 or S8 bearer between SGW and the PGW. And as we know, the combination of all the three logical links is your end-to-end EPS bearer. That's what is happening on the LTE side. We have got one question. IMS deployment is not much. When do you think voice over will take hold in the market? Okay, so IMS deployment. So Verizon is already using IMS. You can go to their website, open development type website, and they are already using SMS and presence. AT&T has started using that in their network for some other services. So IMS is now becoming more and more popular. Some countries in Asia, they have been using IMS for several years. In my opinion, sometime 2012, next year, you should see a lot of use of IMS, because you will see a lot of UE handsets, the real LTE voice handsets becoming available. So at that point, you should see significant uptake in the use of IMS network. So IMS is now becoming reality, but beginning next year, you should see a much more widespread use and deployment of IMS. So voice over LTE, the next couple of years, there should be a lot of activity in that area. Okay, in terms of what we are actually using on the air interface between UE and the A node B, we have signaling, radio bearer, that is SRB. We have two signaling radio bearers. This is basically, for all practical purposes, radio network signaling. This is pretty much core network signaling, non-access stratum signaling. This is the other one is access stratum signaling. So we have that. Then we have IMS or SIP signaling. We have data radio bearer. But the QCI is quite, we need, this is for default connectivity with IMS network. For call setup signaling, we have QCI 5. Okay, again data radio bearer. AM is just RLC mode, radio link control mode, acknowledge mode. Meaning we will do retransmission at the RLC layer if required. Okay. So acknowledge mode data radio bearer for signaling messages. And then we have unacknowledged mode RLC. For the actual voice over IP traffic, and that would be related to QCI number 1. So a given UE has many radio bearers over their interface, right? So you have two signaling radio bearer, one here, one here, one here. But we have 5 radio bearers. Then we have a simple voice over IP call going on. A lot of radio bearers. Just one voice call. One voice call, lot of radio bearers. Okay. Okay, time for a question. I will give you a couple of minutes. So we have this IMS user, we want to connect with serving what? Who is in Okay, LTE access. Okay. Security. Okay. Okay, now let me rephrase the question. Okay, let me modify this. Not must, may. Replace must by may. So, an IMS user may establish a security association with what? Security association. So let's say you want to encrypt signaling messages. Okay. You want to encrypt SIP signaling messages. So who does encryption of SIP signaling messages? HSS, serving, or proxy, CSCF or DNS. So encryption, if you want to encrypt signaling messages, who can do that? I will give you a hint. Whichever IMS element the UE first comes in contact with. If you are a UE, who will be the IMS node you will first talk to? That is the one with whom you may have security association. And it's always there, whether you are in the home network or you are roaming, it's always there. That is the Forrest Gump. That is Forrest Gump. Okay, so correct answer is proxy. Proxy. So proxy is in charge of providing security as far as SIP is concerned. Okay, so SIP signaling between the UE and the proxy could be encrypted, could be secured. Okay, and again, the reason I said do not worry about must is it is implementation specific. So we may or may not have encryption. Okay, it is up to the operator policy to really implement that kind of security or not. Okay? But it is available as an option. Okay, another question. So breakout gateway control function, BGCF, breakout gateway. So do we use that when we have to break out of IP and go to PSTN? That's the question. So do we use BGCF when we need to talk to PSTN? Or it is required for all the voice or IP calls? BGCF. Is it required only when we talk to PSTN or is always there? Break out. So the key word here is break out. Breaking out of the IP domain. Breakout gateway control function. I will give you 1 minute to finish up this one. Okay. Okay, very good, very good. It is true. Breakout gateway control function. Only you are breaking out of IP, going into another domain such as PSTN. Only in that case we need BGCF. You need media gateway control function. You need media gateway only when you are talking to a non-IP domain such as PSTN. If you have just IP to IP call, one UE to another UE, all IP, then you do not need BGCF, MGCF, media gateway. Packets can directly go between UE, eNode B, SDW, PGW, the internet, and then PGW, SDW, eNode B, and the UE, like that. Okay. So, the next topic for us would be supplementary services, but let's take a break before that. We are doing very well in terms of time, so we can afford slightly longer break, maybe 12 minutes instead of 10. So we got a question about this breakout gateway control function. So from, let's say, LTE to PSTN call, right? So we will use the help of breakout gateway control function. Like that. And if we have the other situation, PSTN, then it will be NGCF, signaling gateway, and we can figure out who the serving CSCF is by using the help of interrogating CSCF and HSS. And then we can reach our UE. Okay, so that is basically the UE originated and UE terminated call. Okay, so let me give you an opportunity of using the audio bridge. So if you want to ask a question using the audio bridge, feel free to do that now. So *7 unmute, *6 mute, *7 unmute. I will wait for 30 seconds. Okay, no questions through the audio bridge. Then please continue using the Q&A box in the live meeting. We will now resume with our discussion of voice or IP support using LTE and IMS. Okay. Now, part of a question that we got was why IMS is not much deployed at this time. Basically, cost and complexity. Okay, you have to invest in the brand new network. That you have all these entities, and so you need to have money to do that. And as time passes by, as LTE becomes more and more widespread, then we will see a lot of IP-based services, and at that point, probably it would be cost-effective to start using IMS. So it's just enough mass. We need enough critical mass to make IMS more popular. But in the next couple of years, that should happen. Okay. So now there is another topic here: supplementary services and SMS. So if you want to support those services in the IMS domain, then what do we do? So basically, our UE can communicate with some application server and get all those services, whatever supplementary services we want to provide. So recently there has been some standardization effort. So Ericsson originally started this mobile multimedia telephony, and then now it has gained some traction. So basically, it specifies ways of implementing variety of supplementary services. So examples, let me give you examples first. So here are some examples that we are aiming for. Originating ID presentation, so whoever is the calling party, that number will be presented. Terminating ID. Restriction, if you want to not show such a number, then we can restrict that, we can block. Then diversion, okay, so you are transferring call somewhere, so this is like call forwarding. Okay, unconditional, meaning all the calls are forwarded from, let's say, your cell phone to your work phone, from work phone to cell phone, vice versa. Maybe you are not logged in yet, so in that case, your call will be forwarded. If you're talking to someone else, then call will be forwarded to some answering machine. If the power of the U is off, then we will have the again call forwarding to answering machine because the user is not reachable, or maybe the phone keeps on ringing and nobody replies, so that is the call forwarding when there is no response from the user. Similarly, you can restrict what calls are allowed and not allowed. All incoming calls, if you want to bar, you can do that. All outgoing calls, you can do that. International calls, you can bar. So roaming, so when you are roaming, maybe we do not want to pay roaming charges, then we have not subscribed to such roaming services, so then incoming calls will be barred. Communication hold, putting someone on hold when you are already talking to someone else. If someone has left a message for us on the answering machine, then it is here. Then communication waiting. Some party is waiting for the call, and you can create a conference call in an ad hoc fashion. So those are some examples of the supplementary services that we are aiming to provide in voice over LTE approach. Now, to do that, the main method of doing that is use some kind of application server. This could be plain vanilla flavor where it is only supporting a regular voice or IP call, or now we can start supporting many supplementary services. So the basic idea here is that application servers are able to use existing SIP messages to support all the variety of services that we just mentioned. The user, let me give you one example. Let's say we want to use some kind of prison service. Like Yahoo or Skype. So then what we can do is we can do the registration with that service, and then whoever is online would be shown as part of the buddy list, right? Our friends are all shown online if they are there. You can add friends, add members to your IM presence list, so that what you can do through configuration, you can log on to some website and add members to your buddy list. So that's this membership. You can subscribe to different groups. You may have different kind of triggers. Someone does the registration, then you will get a notification, things like that. So that's that. And HSS will know about the subscription. So our serving CSCF will get subscription information, authentication information, profile for the subscriber, or IMS services. Okay. So all that information we can get through the existing interfaces, IP-based interfaces, and diameter is the protocol that we will be using our SHNCX interface. So the basic idea is that we will use some configuration protocol, XCAP, XML configuration protocol, so we can update the membership, we can update the buddy list, etc. And other than that, we already know the communication between you and the proxy. We know that as part of the IMS registration, the serving CSCF is determined, and as part of IMS registration, the authentication is there. So we are familiar with other aspects of this. So the only thing that is really new here is existence of this application server, which gives us those services. So standardization is a work in progress to define those services and exactly how to implement those. Okay. SMS. So there are different ways of supporting SMS. Let me summarize those. Okay, so SMS, short message service. So we have IP-based approach, and we have non-IMS approach. Those are the two main approaches. Okay. In this session, we are talking about this IMS-based approach, where our UE communicates with the IMS network to access the SMS network, and we can send and receive SMS. In the non-IMS approach, there is LTE, EPS. In the non-IMS solution, our UE just communicates with LTE, EPS, and we have MME talking to the legacy technology, circuit switch technology, could be 1X, GSM, UMTS, whatever, and this is connected to SMS network. So here we treat SMS like a regular circuit switch service, and then we use this new interface between the MME and legacy circuit switch network. So this way we can send, receive SMS, but we are actually communicating via LTE air interface. And signaling messages that we exchange between the UE and the MME that can contain SMS. So that is one approach. So this we will cover later in another session. And today we will look at the IMS-based approach. Okay. Now, we will have some previous registration with the HSS. So there is some application server here. This is some application server that is in charge of SMS, and it will register with the HSS. So HSS now knows that we have an application server that is able to support SMS. Next, our UE has done the IMS registration in the past. Okay, so it means we know about the proxy, we know about the serving. Now what do we do? Now our UE has already established some kind of bearers, EPS bearer. So that is already in place. So we have the radio bearer, S1 user plane, everything exists. Radio, S1 user plane. All the logical links are already there as part of the bearer setup. So whenever UA wants to send an SMS, it will send a message, a SIP message called message. That is the name of the SIP request, like invite. Just like we have invite SIP request, we have so-called message request, and inside that we will have some fields. So there is a so-called vnd.3gpp.sms, and inside that payload we have actual SMS present. Now it will find its way. This is SIP signaling, and if you recall, SIP signaling is treated like user traffic. And this traffic will go to the E node B, and then serving gateway, and the PGW. So now it has reached the serving call session control function. Then we look at the destination. Okay, here is the destination of that message. IP short message gateway. So the serving CSCR forwards that SIP message to the IP short message gateway. And this is the one that interfaces with the service center. SMS service center. So this SMS center would be then delivering to the destination. So here the UE is the sender. It's called short message over IP sender, because in this case the UE has originated the SMS. If it is a UE terminated SMS, then it's exactly the opposite. The service center, SMS service center, would send a message to the application server, because the HSS knows that this application server is capable of supporting SMS. So then from the IP short message gateway, the message will find its way all the way back to the UE. So here we are using LTE interface, and over the LTE interface, instead of a voice or IP packet, an IP packet containing a SIP request call message is transmitted, and that's how we can take care of SMS. And the traditional means of sending the acknowledgements, reports that your message has been delivered, all those things are also supported. So whether there is a delivery report for SMS or there is actual SMS, we have both included in the SIP message. So that is how we can support SMS in the IP domain. Any question on SMS? Okay, no question. Okay, so time for me to ask you a question. I will wait for a minute or two. Oh, we got several questions. Thirty seconds. Please participate in the polls. We have about 27 so far responding to the poll. Very easy. True or false? Who provides supplementary services? Ten seconds. Okay, let's share the results. Okay, almost 80% got it right. Supplementary service is not provisioned by breakout gateway control function. Okay, so we have an application server. Let's say MMTEL application server, some kind of voice or IP application server. That is the one that will give us supplementary services. A BGC, a breakout gateway control function, is when you are getting out of IP domain and trying to reach PSTN. Then BGCF will help us find a media gateway control function so that we can have eventual connection with the PSTN. Okay. Another question coming your way. I will give you 30 seconds. And there was a question in the Q&A box. So yes, let me share the results here. Yeah. So yes, application server indeed acts as an IP short message gateway, and in the PDF file that you have, you should have a list of all the references. And if you want more than that, just send me email and I will send you additional references. But yes, we do have standardization, we do have specifications on that. There are several specifications that give details about SMS implementation. Looks like there is one more question. Oh, are there actually any vendors? So actually, any vendor, right, a traditional core network vendor can build. So probably you would also have these kind of gateways available. Cisco would be another example. They would have these kind of gateways. Now, these are like core network entities. Right? They are some kind of gateways that can process SIP signaling messages, etc. So it's not complex to build those, especially when you follow the 3GPP specifications. That should not be too complex a task. So anyone aware if you already are building this kind of gateway? Probably you are. So if you are aware, please let us know. Okay. So today we looked at the IMS architecture. So inside the IMS architecture, we have call session control function. So we have three kinds. We have proxy, we have interrogating, and we have serving call session control function. Home subscriber server, media gateway control function, media gateway, and signaling gateway. Proxy would be the first point of contact of UE with the IMS network. The proxy can help us with the quality of service control because it works with PCRF. Proxy can do SIP compression. Proxy can activate security with the UE, things like that. Interrogating, it is asking HSS who is the serving CSCF, and serving is in charge of the session. So when a SIP message is received at the serving CSCF, it decides what to do next. Should it go to the media gateway control function, breakout gateway control function? Should it go to directly some IP domain? So all those decisions are made by serving CSCF. Serving CSCF is in charge of the session. HSS, the home subscriber server, that is similar to what we saw for LTE. So here for IMS specifically, it will help us with IMS authentication. It will provide authentication information to the serving CSCF, and also it will help interrogating CSCF decide who is the serving CSCF is. Media gateway control function basically is converting between SIP signaling and ISUP signaling. So an example would be invite message and initial address message, like that. So that's media gateway control function. Media gateway, there's the real traffic. So on one side you will have voice or IP. On the other side you will have something that PSTN can understand. SDW is just the signaling gateway. Basically it is converting the IP into lower layers of SS7 message transfer part. Voice or IP protocol, we looked at the main functions of SIP, STP, RTP, RTCP. SIP basically is your signaling. So your call setup, modification of the call, tear down of the call, whatever you want to do, that all call related signaling is done via SIP. Session description protocol that describes basically the quality of service, what kind of speech codec we will use. For example, AMR speech codec with this kind of data rate. So that is in the STP. Real-time transport protocol that is helping us carry the actual voice or IP traffic, and it is running over UDP. The reason for UDP is we want to reduce delay, we want to reduce overhead. We do not want to do retransmission for actual voice or IP traffic. Otherwise, there will be long delay and quality would be quite bad. So no retransmission at that layer. The control protocol, RTP control protocol, this is used in LTE when the media is placed on hold. This is just as a keep alive mechanism, making sure that the connection is already there. We have voice or LTE. This is a marketing term basically, and it means that we are using the technical features defined by so-called one voice profile. An example is already here, AMR 12.2 kilobits per second, bus channel compression for compressing the IP headers, things like that. So everybody follows the one voice profile recommendations, and now we have interoperability between the UE and the network. Examples of supplementary services: you can restrict call, place the communication on hold, you can create a conference call. SMS, you can support using IMS. We saw that approach in this session. Another session we will talk about a non-IP approach to support SMS. Before ending the session, I will just mention briefly supporting voice. Okay. So there are different ways of supporting voice. If you are using LTE, this is what we discussed today, voice or LTE. I'm summarizing the main approaches, and then we have another approach called CS fallback. So we'll talk about that in another session. Circuit switch fallback. So here we are relying upon legacy technology for a voice or IP call. So those are the two main approaches. The handsets should be available 2012. Okay. Then you can expect voice or LTE to become more popular at that time. Right now, we have data cards available for LTE. Okay. So there is no support for voice. You can do Skype or Yahoo type voice or IP, but there will not be any QoS control. Okay. If you want strict QoS control, then you need IMS. Oh, we got one question. Yes. So IMS supports the IPv6 and IPv4. In fact, when the IMS was initially defined, it only supported IPv6. But because IPv4 is so widespread, they removed the IPv6 mandate. And now IMS supports both IPv4 and IPv6. Both are supported. So right now there is no voice, no voice or IP. But as I said, beginning next year you should see voice or LTE being used. Okay. So those are the two main things, and we have support for handover from one technology to another, LT to CS. That is called single radio, voice called continuity. So we will talk about those in another session. Okay. Any questions? Related to voice or LTE? Okay, so thank you for your questions. And Peggy, if you could please provide the evaluation form.